Okay, so when I say the word volcano, what's the first thing that pops in your head? Probably destruction, right? Lava, ash, just chaos. But what if I told you that's only like half the story? Because today we're going to look at how these incredible fiery forces and the slow, unstoppable grind of tectonic plates are actually the planet builders. They're the architects of our entire world. Yeah, we tend to focus on the destructive side, but the truth is, without them, our planet would probably just be a dead, barren rock in space. Volcanoes are the original world builders. And to understand how, we've got to rewind the clock way back, billions of years ago, when the Earth was just starting to figure itself out. So let's get into it. How does a planet even go from being a molten ball of rock to a world with oceans and an atmosphere? Well, the answer was literally vented from deep inside the Earth itself. It came out through countless volcanoes, giving our young planet its very first breath. And this comparison right here shows that transformation perfectly. If you look at the left, back in Earth's early days, you've got volcanoes just pumping out all these gases that were trapped in the mantle. Water vapor, carbon dioxide, nitrogen. Now, look over to the right at the present day. The process is pretty similar, but you'll notice one crucial difference: oxygen. That's the big one, and it's a byproduct of life, something that wouldn't show up for a long, long time. So this whole process, it's called outgassing, and it's basically what laid the entire foundation for a habitable planet. All that water vapor they were releasing, it eventually cooled down, condensed, and rained for centuries, literally forming the very first oceans. And meanwhile, the heavier gases like nitrogen and carbon dioxide, they stuck around, creating our very first primordial atmosphere. Okay, but this all raises a pretty huge question, right? What is this incredible, unseen power source that's been driving billions of years of volcanic activity and is still powerful enough to shift entire continents? Well, to find that answer, we've got to go deep, deep inside the planet to find the engine room. And the answer is right here. It's in the mantle. See, the Earth's surface, what we call the lithosphere, it isn't one solid piece. It's actually broken up into these massive tectonic plates that are always on the move. And they're basically floating on a hotter, kind of softer layer called the asthenosphere. The best way to think about it is like giant rafts of rock floating on this thick, super slow-moving sea of semi-molten material. The process driving this is called mantle convection, and honestly, the best analogy is a colossal, super slow-motion lava lamp. You've got hotter, less dense rock deep in the mantle that rises up. As it gets near the surface, it cools off, gets denser, and then sinks again. This massive circular flow creates an incredible force that pushes and pulls on those tectonic plates floating above, dragging them all across the planet's surface. So what's fueling this incredible engine? It's not some giant fire down there. It's actually nuclear energy. We're talking about the slow, steady decay of radioactive elements like uranium and thorium that are just scattered all throughout the mantle and crust. And for billions of years, this decay has been releasing heat that is the primordial warmth that keeps our planet geologically alive and kicking. For decades, this whole idea of continental drift was seen as a pretty wild theory. It was almost science fiction. Scientists needed cold, hard proof, a smoking gun, if you will. And they ended up finding it in just about the most unlikely place you could imagine: the bottom of the ocean. I mean, how could you possibly know the seafloor is moving? It was a huge puzzle. It's not like you can just watch it happen. The big breakthrough came when scientists started mapping the magnetic properties of the ocean floor. And they uncovered this pattern, a pattern so perfect and so bizarre that it could only have one possible explanation. And this is the pattern. This is the key. What you're looking at here is a map of something called the Juan de Fuca Ridge, just off the coast of Washington. And you see those alternating dark and light stripes? Each one represents a period when Earth's magnetic field was either normal, like it is today, or completely reversed. It's a perfect, symmetrical barcode written on the seafloor. So here's how it works. As new magma rises up at that mid-ocean ridge and cools, it's basically like a tape recorder. The little iron-rich minerals in the rock act like tiny compasses, and they lock themselves into alignment with whatever the Earth's magnetic field is doing at that exact moment. Then, every few 100,000 years or so, the Earth's poles flip, and the next batch of new crust that forms, it records the new direction. This creates that perfect, mirrored timeline on both sides of the ridge, proving without a doubt that the seafloor was spreading apart. This was it, the smoking gun. So, with that great mystery finally solved, we can zoom out and look at the big picture. This internal engine, this spreading seafloor, it's all part of a huge, interconnected global system. It's like a slow, incredibly powerful dance of tectonic plates that has been reshaping the face of our planet for eons. And this diagram really puts the whole system into motion. You can see right here, new crust is forming at this oceanic ridge, and that's pushing the plates apart. Then, if you follow that plate over here, you can see it diving, or subducting, as geologists call it, underneath a continental plate. And that process is what carves out those super deep ocean trenches and fuels the creation of volcanic island arcs. So really, all the action happens at these plate boundaries. Where plates move away from each other, that's a divergent boundary. That's where new crust is born. But where they move toward each other, a convergent boundary, that's where they collide. And a collision like that can do one of two things. It can either crumple up and build massive mountain ranges like the Himalayas, or one plate gets forced down and recycled back into the mantle, triggering some of the most powerful volcanoes and earthquakes on the planet. Okay, so this is all really cool, but it's not just some abstract geology lesson. This massive, planet-sized process of creation and destruction has a very direct impact on all of us, on our civilization. Why? Because it's also responsible for creating and concentrating many of the essential resources we rely on every single day. Yeah, it turns out that these different tectonic settings are kind of like geological factories that specialize in making specific metals. For example, that immense heat and pressure you get where a plate is subducting and melting, that's the perfect recipe for concentrating things like gold and silver. Meanwhile, those spreading centers at the mid-ocean ridges, they create these rich deposits of copper and zinc. And you can see exactly how this works on this map. All this movement, this melting and remaking of the Earth's crust, it isn't just building mountains and volcanoes. It's also a massive, planetary-scale sorting and refining process. It's taking tiny trace elements from huge volumes of rock and concentrating them into the valuable mineral deposits that have literally fueled human progress for centuries. So the next time you look at a mountain range, or maybe see a news report about a volcanic eruption, just remember the immense, patient power that's at work beneath your feet. The very same engine that gave us our oceans and atmosphere is still running today. It's constantly reshaping our world, and it's forging the materials of the future. The planet, it seems, isn't finished building yet.